Let us start today's lecture. In today's lecture, we are going to start with a topic on effect of changing voltage on torque speed characteristics curve. Here, changing voltage means changing supply voltage. Suppose we have an induction motor. This is the side view of an induction motor, three-phase induction motor. When we give three-phase supply, from our previous theoretical background, we know there will be creation of rotating magnetic field, north pole and south pole, and this magnetic field will be rotating. When the magnetic field rotates, it cuts the rotor windings or rotor bars. Eventually, EMF is induced in the secondary side. Now, this induced EMF depends on some factor, that is the speed of the rotating magnetic field, which is constant for a constant supply frequency, and also the magnetic field. This is the magnetic field strength. This magnetic field depends on the supply voltage. If we increase the supply voltage Vs, then what will happen? The field strength will also be increased. If we decrease the supply voltage, the field strength will also be decreased. Remember, changing supply voltage does not affect the change in the speed of the rotating magnetic field. Whenever we increase supply voltage, the magnetic field strength increases. Now, when magnetic field strength increases, what happens? For the same rotational speed, the induced EMF E2 will also be increased. So we can say supply voltage is proportional to E2 prime. What is E2 prime? E2 prime is the induced EMF in the rotor side at standstill. Whenever the supply voltage is increased, the induced EMF in the secondary side will also be increased. Whenever the supply voltage is decreased, the induced EMF in the secondary side will also be decreased. This is clearly understandable from our previous theoretical knowledge. Here we considered linear zone of the supply voltage versus magnetizing curve. For example, for any solenoid, if we increase supply voltage, which will increase the current eventually, the magnetic flux is taken in the y-axis. If we increase this current, initially it will increase linearly, later on it will move to the saturated zone. When we are saying that Vs is directly proportional to E2 prime, actually Vs supply voltage is proportional to this phi, and this phi is proportional to E2 prime. And this Vs versus phi, actually when we increase Vs supply voltage, the current will also be increased for a particular solenoid. So phi will be increased proportionally in this region from here to here. So we are considering this linear zone. But when it moves to the saturated zone, it's not true. So if we consider this question, Vs is proportional to phi and phi is proportional to E2 prime. So we can write Vs is proportional to E2 prime. That's what we wrote here. I hope now it is clear that for this relationship we are considering only this linear zone. Now let us write the running torque equation that we derived earlier. Tau equal to 3 over twice by n s into E2 prime square divided by R2 square plus Sx2 prime square. Now this portion is constant for a particular speed. The S value, slip value is constant, and if we consider all other values are constant, then we can write the running torque is directly proportional to E2 prime square. As we said that our supply voltage is proportional to E2 prime, so we can write torque is proportional to the supply voltage square. So this is the relationship between torque versus supply voltage. Oh, here I forgot to put R2. Even though we have R2 here, this relationship is valid. From this relationship, we can see that if the supply voltage is reduced by half, Suppose we are giving half of the previous supply voltage. So from this equation, the torque will be reduced by square of this value. That means it will become 1 by 4 of Vs square. So torque will be reduced by 1 by 4 times. If we double the voltage, the torque will be increased by 4 times. So you should remember that for small decrement of the voltage, the torque will be reduced drastically, and for a small increment of voltage, the torque will be increased drastically. It's not linear, rather square of the incremented or decremented values. Now let us plot the torque speed characteristics curve for different supply voltage. This is NR, tau R, and for a particular supply voltage, suppose the torque speed characteristics curve is this. Here we have NS. This torque speed curve is for Vs1 supply voltage. Now if we decrease the supply voltage, what will happen? The torque value will also be decreased. So the curve will look like this. This is for another supply voltage which is less than Vs1, and this decrement will follow this equation. This is tau S1 and this is tau S2. Now for a particular loading condition, for example, this was the loading condition. Initially when we were supplying Vs1 voltage, then the corresponding speed was here. Suppose this is NR1, and when we reduce the voltage for the same amount of load, the motor won't be able to produce that much of torque with this speed, so it will start reducing the speed, and it will have the intersecting point here, and this will be the new rotor speed where NR2 is less than NR1. So if we decrease supply voltage, the rotary speed also decreases. If we increase supply voltage, rotary speed also increases, and they will be following the new torque speed characteristics curve, and intersecting point of the load curve and the characteristics curve will give us the operating point. Now if you plot the same using MATLAB, as I showed you in the previous lecture, we'll get this similar type of characteristics curve. I want all of you to reproduce this curve using MATLAB coding that we developed in our previous lecture. Next we'll discuss on effect of changing supply frequencies on torque speed characteristics. If we rewrite the torque speed characteristics equation, that is tau r equal to 3 over twice pi ns into s into e2 prime square into r2 divided by r2 square plus s x2 prime whole square. So this is the torque speed characteristics equation. Now when we change the supply frequency, the parameter that is changed is ns, also x2 prime, because ns equal to 120 f, where f is the supply frequency over p, and x2 prime equal to twice pi fl. As we are considering x2 prime at standstill, so f will be equal to supply frequency. So these two parameters are dependent on the supply frequency. Now if we increase supply frequency, both these parameters are increased. As both these parameters are at the denominator side of the equations, by increasing supply frequency, the value of tau will be decreased. Now let us see how the torque speed characteristics curve looks like. Let us draw the torque speed characteristics curve. This is y-axis where we are going to take tau r, and this is x-axis where we are going to take nr. Suppose this is the torque speed characteristics curve for supply frequency F1. This is ns. This is starting torque, tau s1. Now, if we increase supply frequency, the value of ns and x2 prime both will be increased. Once ns is increased, that means ns point will be higher than this point. So this is my new ns. For example, this is ns2 and this is ns1. As ns and x2 prime both are increased, the magnitude of tower at every point will be decreased. So the curve will look like this. We'll plot using octave and we'll see our result, but I want all of you to understand how the things are happening. Only for changing the supply frequency, this ns value changes. The other parameter changing that I showed in the previous pages, there you won't find the change in ns. So this is the case for f2, where f2 is greater than f1. Now if we redraw the same for lower frequency than the f1, suppose frequency is decreased, then ns will be decreased and x2 prime will also be decreased. As ns and x2 primes both are decreased, what will happen at each and every point? Tower will be increased. So ns3, suppose this is the ns3, this will be decreased, but the magnitude of tau will be increased, so the curve will look like this. So this is the case. So we have this case for f3, which is less than f1 and definitely less than f2. So these are the case we are going to get for changing supply frequencies. The characteristics curves were plotted using octave for different frequencies, and we have got the figure like this. In x direction we have taken nr, in y direction it's tau r. Now this is the case for f equal to 50 Hz. This is the case for f equal to 60 Hz, and this is the case for f equal to 70 Hz. We can see we are getting similar type of patterns as we got here. I want all of you to resimulate this torque speed characteristics curve for different frequencies, modifying the code that I showed in the previous lectures. Next, we'll figure out the condition for maximum torque under running condition. Previously, we got the condition for maximum starting torque, and that was R2 equal to X2 prime. Now, in order to get the condition for maximum torque under running condition, we need to analyze the torque equation under running condition, that is 3 over twice pi ns into s into e2 prime square into r2 divided by r2 square plus s x2 prime square. Now if we plot this, we know the curve will look like this. This is nr versus tau r, and the curve looks like this. This is 0, this is ns. Now if we consider with respect to s, then s will have decrement value if it goes to the higher value of nr. That means s equal to 1 here and s equal to 0 here. Now in order to get this peak, we need to differentiate this curve with respect to s. That means we need to differentiate this equation with respect to s, and at this point differential value will be 0. So we need to write d tau r divided by ds equal to 0 in order to get this peak point and in order to get the condition for maximum running torque. So if we write this equation elaboratedly, ds over ds into tau r will be 3 over twice pi ns into s into e2 prime square into r2 divided by r2 square plus s into x2 prime square, and equate them equal to 0. If you solve it, you'll get R2 equal to S x2 prime, and this is the condition for maximum torque under running condition. I want all of you to solve this from here to here using your knowledge on solving first order differential equation. You'll get this. From this equation we can write S equal to R2 over x2 prime. So this is the condition for maximum torque. Now what is the equation for maximum torque? In this equation, if we put S equal to R2 over x2 prime, we'll get the equation, corresponding equation, tau R equal to 3 over twice pi ns. If we write, instead of S, we'll write R2 over x2 prime into E2 prime square into R2 divided by R2 square plus R2 divided by x2 prime into x2 prime whole square. If we simplify this equation, we'll get this equal to 3 over twice pi ns into e2 prime square divided by twice x2 prime. And this is the equation for maximum torque. For this case, we can write tau r max, because we are putting s equal to r2 over x2 prime, which is the condition for maximum torque. So the tau r max can be expressed as this. Next, we'll discuss on effect of rotor resistance on rotor current. From our previous lectures, the rotor current can be written as I2 equal to S into E2 prime divided by root over R2 square plus S x2 prime square. For a particular rotor resistance, we'll get this type of curve. In y-axis we are taking I2, and x-axis we are going to take NR, that means rotor speed. So the curve will look like this for R2. Now if we increase the resistance, rotor resistance, the starting torque will be increased, but the current will follow this path. This point is in a synchronous speed. Here this is for R2 prime, which is greater than R2. This is starting current IS2, and this is IS1. Now if we keep increasing the rotor resistance, the curve will look like this. This is for R2 prime, which is greater than R2 double prime, which is greater than R2 prime, and this is IS3. We can see if we increase the rotor resistance, this is the starting current, because here NR equal to 0. We can see the starting current decreases. Generally, when the motor starts, it draws huge amount of current. Now if we want to reduce the starting current, what we can do, we can increase the rotor resistance. By increasing the rotor resistance, we can decrease the starting current. And if we have the running speed with a particular value, for that particular running speed we can figure out what is the current under running condition. So this is the current under running condition. We are considering rotor current here. Remember, rotor current and stator current, they are proportional because they are following the transformer principle. So if the current in the secondary side increases, then current in the primary side will also be increased. Reducing starting current is an important feature for on-rotor induction motor case, because sometimes higher starting current causes the damage of electrical equipments. So for starting purpose, by exerting rotor resistance, we can reduce the starting current. So for starting of an induction motor, adding resistance in the rotor side is always advantageous in terms of current consumption as well as in terms of starting torque. This feature is only achievable for on rotor case. This is how the external resistances of a on rotor type induction motor are added. At starting, the handle of the rheostat is set in the off position so that maximum resistance is placed in each phase of the rotor circuit. This reduces the starting current and at the same time the starting torque is increased, as we saw in our previous pages. As the motor picks up speed, the handle of the rheostat is gradually moved into clockwise direction and cuts out the external resistance in each phase of the rotor circuit. When the motor attains normal speed, the changeover switch is in the on position and the whole external resistance is cut out from the rotor circuit. I hope this is clear to all of you. We'll continue in the next lecture. Thank you.